Hello, this is Nachum Danzig, and today we are discussing operating systems, and particularly Chapter 8 of Silverschatz's book and memory management. The basic thing everybody has to understand in management is that every process, as you can see in this diagram, is got its own location in memory. In this case, we see the operating system is in the beginning, and then each process has its own section from, for example, 256,000 to 300,040 is the first process. And all of his code and his arrays, all of the things that he wants to access in memory are going to be confined to that area. And another process will be in a different area. And this will give us the ability to protect the code or the data of a particular program, a particular process, from another process. They shouldn't have access to each other. And there's special hardware that does that. It's actually, and it uses something called a base register and a limit register. Basically, it checks, it says any access to a memory location, let's say for the second process here, has to be above 300,040 and below 300,040 plus this limit, 120,090. So in other words, it has to be within that range. This is like the added amount of addresses that you can go to, which is, in other words, until 420,940. So that's like an extra space of this amount. So that's the limit register, how far it can go from the beginning. And any attempt to access memory at a location beyond that point or beneath the base register will be a hardware error. Okay, that's the basic idea of base and limit registers, which prevent me from accessing memory I'm not supposed to. Now we're going to talk about strategies for allocating the memory. Allocating means deciding where the operating system has to decide where a particular process will have its memory stored. And not everybody can be at the beginning of the memory. Some people will be in one place, and some processes will be in another place. So the first method is going to be a contiguous method. So in other words, a contiguous memory, which means all the memory of a particular process will be in one spot, not spread out. And that's what we saw exactly in this picture. So let's talk about contiguous. So each process is contained in a single contiguous memory area. That's what we just said. And we have something called a relocation register, which is used to, really it's kind of instead of this base register. I think I have a picture of it here. Yeah, look at this picture. So we have, it's a little bit different from what you just saw. What we say is like this. We say the CPU creates some kind of logical address, which is a theoretical address that the program understands. The program has decided that, he wants to jump ahead 10. So it's going to be 10 from the beginning. Now we're going to check, is 10 from the beginning less than the limit register? Remember, the limit register, as we saw here, is how much past the base I can go. Well, if the limit register is 120,000, then 10 would be fine. 130,000 would not be fine. So the first thing we check is, this is special hardware that's going to check using registers here. So the hardware will check every time I try to get an address. It'll first of all check, is that logical address less than the limit, less than 10, in our case, 120,000 and something. And 10, of course, is less than that. But if it would be 130,000, then it would give me no, and it wouldn't let me proceed. It would give me some kind of trap. It would stop. The hardware would indicate to the operating system this is a violation. And the operating system would not let it continue. So that would prevent me from going beyond the limit. But now, okay, so it's less than 120,000, fine. But where is it actually in memory? It's not actually at place 10. It's at 10 plus a relocation register. In my example over here, the relocation register would be whatever the base is here. In other words, 300,000 for this second process. So that would be added to the 10, and I get 300,010, and that would be the actual physical address. That's why this plus symbol here. That's the actual physical address that I would actually read. That's the idea of how to locate a location, a memory location, how to translate from the way the computer perceives it to the actual physical location. Okay, so far so good. And that's what's written here. We use relocation registers to protect user processes from each other and from changing operating system code data, right? Also notice in this picture, I'm not going to be able to get to this operating code. So operating system code is I'm going to add my relocation register. The first relocation register will be 256,000. So I'll never be able to get to 0. So, there's the lowest process will not be near 0. It'll be already over here. There's only one relocation register. But the question is, when I'm running this process, the value in it will be 256,000. When I'm running the second process, the value will be 300,000. And when I'm running the third process, the value will be 420,940. And this space is unused as of yet. So those are the relocation registers. And what's written here is that that it will protect the operating system code and also other people's code, because I can't get the hardware will not allow me to get to an address that I'm not supposed to get to. Of course, every time I switch between a process and another process, the operating system will have to change the values in the relocation register and in the limit register. Okay, so the base register contains the value of the smallest physical address, right? That's what and the limit register, well, we don't actually have. This is talking about a different scheme. This is talking about this scheme, where we have a base and limit register. It's slightly different, but if you think about the picture I just showed you, it's a little bit better with a limit register and a relocation register. So again, the base register contains the value of the smallest physical address. The limit register contains the largest offset allowed from the base register each logical address. Fine. The MMU maps the logical address dynamically to the physical by adding the base register or the relocation register. So that's what we're just seeing here. This is essentially the MMU, what it's doing. On context switch, the new base register is loaded by the scheduler into the MMU. That's what I said. That whenever we switch between processes, we're going to change the limit register and the relocation register to be appropriate for that process. Fine. This allows the operating system to use more memory or less when needed, because I can change it theoretically. If there's all of a sudden a need for more memory, I might be able to change the values or even move the program from one place to another if I'm going to do swapping. For example, device drivers may not be needed in the operating system all the time. The kernel code can then be what is called transient, i.e. not always resident. In other words, the parts of the operating system that are not being used, I can keep on disk. And when I need them, I can create space for them. And that's this diagram that I talked about. Okay, so let's talk now more about contiguous allocation. And let's say like this. There's two possible ways that you can partition your disk. You can say like this. You can say that every process gets automatically a fixed size. In other words, every process gets 1,000, or let's say a real number, 100 megabytes or 500 megabytes for each process. And then I know exactly how many processes I can run on my computer system. If I've got a certain amount of memory, if I've got 16 gigabytes, and I can give each one 500 megabytes, then I can have 32 processes. And that's it, no more. That would be a fixed size partition. And then the degree of multi-programming is limited by the number of partitions. In other words, I can't have the degree of multi-programming means how many processes I can have running at the same time. I can't have more than 32. If in the schema, in the example I just gave, as I have fixed sizes. We're not going to talk about that so much. We're going to talk more about the variable size partition, where I can give every process like what I think it's going to need, or what it, I've already got the actual code of the program. So the code of the program is, 5 megabytes. So I know I have to get I have to get 5 megabytes. Maybe it's going to have some dynamic allocation in there. Maybe I'll give it 10 megabytes. I'll give a variable size. Depending on the size of the program, I'll give it a different size. We're not going to actually talk about how the operating system decides how big of a slice to give it so much, but assuming that it has a way of deciding how big each process memory space should be, I can set up a system where process 5, for example, gets a small space, and 8 gets a much bigger space, and 2 gets again a small space. That would be a possible scenario. I've divided up the memory in variable sizes. That means the limit register and the relocation register, would be set accordingly. The limit register for process 8 would be larger than the value in the limit register would be larger than the value in process 5. See here in the book they just say when a process arrives, it is allocated memory from a hole large enough to accommodate it. It doesn't say how big we need it, but in other words, let's say the system goes on and we have 5 and 8 and 2, and now 8 finishes and he's out of the system. Now comes along process 9, and we find this big empty space here, and we'll put process 9 there. And comes along process 10, we'll put process 10 there. And we still have this little space left. Because when a process exits, it freed its space. Okay, so that's our situation. The operating system will have to, of course, maintain information about which spaces are free and which spaces are allocated. In other words, if I want to use process 9's space, I have to know where he begins and what his limit register and what his relocation register is. Same to a process 10. So there's got to be a table in the operating system to maintain all that data. Well, that's fine. But we do have a problem which we have to think about, which is in this diagram, what if a process like 11 comes along and his size is the size of process 8? Well, of course we don't have a place for it. Well, that's fine. But maybe we'll see a different example. Well, we don't have a good example, but you could imagine, let's imagine a different case. Let's imagine that now, after this scenario happens, process 9 finishes. So over here at the end, at the fourth, square here, the fourth, this is sequentially in time. At this certain time, process 9 finishes. So now we've got a hole between 5 and 10, and another hole between 10 and 2. Now, if a process comes that needs a space that's a bit bigger than either of those holes, those gaps, then we can't put it in, but it's kind of frustrating because we actually have that space. There is that space, it's what's called fragmented. It's not all in one contiguous location. Now, we are trying to find a contiguous slot for each process, and we can't because there's a small piece where 9 used to be, and there's a small piece here, and I can't combine them. Now, okay, so that's what we want to avoid. We want to avoid, essentially, little spaces that, get created. So we're going to think about 3 possible ways of choosing where to put a process. One idea is to say, put it in the first hole that is big enough to fit the process. In other words, let's say I need, let's say this space between 10 and 2 is, 100 megabytes, and I only need 90 megabytes. Well, I can put it there, and I'll have 10 megabytes available if there's another program that needs 10 megabytes. I'll put it in the first place. But imagine there was a place at 9. 9 has gone, so there's a gap here where 9 used to be. And there's still this gap here. So which place should I put it? So I could put it in the first one that I see. That's the first fit. The first one I see. Now, if 9 is too small, if the space that was previously occupied by 9 is too small for my new process 11, let's say, then I'll try here, and if it's big enough, then I'll put it here. But if 9 fits, if I can fit it in, then I'll put it in the first place I find. That's called first fit. There's another idea, which is to say, no, put it in the best fit. What the best fit means is put it in the place that leaves the least amount of spare space. So in other words, if I again have 90, I have a 90 megabyte process, and the space that was occupied by 9 is 100 megabytes. And the space that's over here after 10 is, let's say, 95. So where should I put it? In the place where the 100 is, or the place where the 95 is? So best fit says, well, don't put it in the first place you found, which is the first place available was 100. You could fit 90 in there. Put it in there. That would be first fit. But best fit says, no, put it in the place where I'll have the least leftovers. Where the leftover will only be 5 megabytes. Because this place is 95, and when I put in a 90, I'll have 5 unused. So maybe that's where I should put it. That would be saying best fit, which leaves the least amount of unused space. The sliver, the unallocated is the correct term. The unallocated sliver of the smallest size. That would be best fit. Now, there's something wrong with best fit, if you think about it. Because it could be that sliver is only 5 megabytes, and 5 megabytes is so small that it's unusable. Because the smallest, every program wants at least 10 megabytes. So that 5 is too small. So maybe it's better to put it in the worst fit. In other words, in the place that leaves the most space. So I'll put the 90 in the 100, and I'll have a larger sliver of 10 megabytes, which is potentially useful to me in some other program. So that's the alternative approach to thinking about where to allocate a process. So that's what we call here first fit, best fit, and worst fit. Worst fit says allocate the largest hole. Then, of course, you've got to search the entire list to find it. Also, best fit, you have to search the entire list. First fit, you don't have to search the entire list, so it's actually faster. But you may end up with sometimes a big sliver, sometimes a small sliver. Best fit will minimize the sliver. Worst fit will maximize the sliver, the remaining sliver. It turns out that in the analysis that people have done, first fit and best fit are better than worst fit in terms of speed and storage utilization. In other words, it actually turns out that this idea of worst fit is not such a great idea. Leaving these, in other words, we're anyway going to end up with slivers that are not so nice and not so usable. So we may as well put it in the best fit and keep the largest spaces available for future use. Okay. So what I just talked about, these slivers, is actually called fragmentation. And that's what this slide says here. What that means is, well, fragmentation means that if this process keeps on going, and I keep on taking in processes and out processes, in processes and out processes, I may have lots of slivers that are unusable. And that's called external fragmentation, which is written here. The total memory space does exist to satisfy a certain request, but it's not contiguous. It's several slivers spread out. And therefore, it's lots of little partitions. And therefore, it's unusable. And nobody's allocated to it, but nobody's been allocated it, but it's unusable. So we're in a kind of a frustrating situation where we have the space, we can't use it. We call that fragmentation. The disk has become fragmented. There's lots of little fragments, or the memory has become fragmented. Now, there's something else called internal fragmentation, and that's when let's say we decide that we're going to give every process memory in units of 10 megabytes. So a process that needs 11 megabytes, we're going to give it 20 megabytes because we can't give it less than 11, and we always give it in units of 10, even though it only needs 11. But we're going to allocate it, and we're going to allocate every process in units of 10. You need 80, fine. You need 83, we'll give you 90. Whatever, then we'll have something called internal fragmentation, where internal to the allocation of a particular process has been allocated 90 megabytes, but he only needs 83. So there's 7 megabytes of internally fragmented memory. It has been allocated, but in a wasteful manner, in a manner that the process doesn't need it. Okay. what is the solution to these fragmentations? So, well, internal fragmentation, we're not going to talk about yet, at least, but that's kind of a problem that's you could avoid just by having instead of saying everybody gets a unit of a multiple of 10 megabytes, we could say every process gets a multiple of 1 megabyte or a half a megabyte. We could reduce internal fragmentation that way. But how do we reduce external fragmentation? All these slivers. So the answer you may have thought of already, which is to do something called compaction. You basically, if you go back to this picture here, imagine that again 9 has gone out, and there's just 5 and 10 and 2 here. So we might slide down 10 till it's adjacent to 2, and relocate it, and copy all the data down to a location adjacent to 2, and then we'll have 2. Then instead of having 2 small areas, we'll have 1 big area that's available. That's called compaction. So we push the memory together, and that will avoid what's called external fragmentation. The problem with compaction, which you should think about, is that it requires a lot of time. I've got to copy everything. I got to copy all the memory to new locations. Also, it's only possible if address binding is not done at compile time or linking time. It has to be done dynamically. We talked about this in other lectures. The address binding has to be dynamic. Well, that's pretty much common strategy nowadays. So that's not such a problem. But certainly the time is a problem. Compaction is not a good solution because it takes a lot of CPU work to move memory locations. Another solution would be to allow process memory to be non-contiguous and then scatter it throughout the memory. And we'll talk about that. In other words, another solution would be to not have it contiguous and assign a bunch of slivers to one process. We'll see how we do that. Here I say that the backing store also has the same fragmentation problems as the disk. Can also have these similar kinds of fragmentation. Okay. So one solution or one idea is instead of allocating, like we did over here, back to this picture, I keep going back to this picture, instead of allocating a large area to a process, we could actually divide the process into segments. And then, since the process is got small segments, we could more likely find a potential sliver to use. I guess that's the motivation for segmentation. Although segmentation is finally not going to be what we do nowadays, but we'll talk about it anyway because it is a theoretical solution. And segmentation says like this: a program is not just one monolithic thing. It's composed of all kinds of different things. It has arrays. It has main memory, main program. It has functions and procedures. It has objects. It has local variables, global variables. There's all kinds of different types of things. So we could make a segment for each thing. In other words, we could look at a program and say all of the main program flow will be in this memory location, and all of its stack manipulations will be in this memory. All of the functions that it calls will be over here. A square root like library functions, maybe, which are linked into the program, will be in a different location. So each of these, the whole program has got all this memory, but it's really composed of sections or segments of memory, which have each their own starting and ending point. And then we can take the physical memory and say, this section, what was that? 1 was, let's say, subroutines. The subroutines we'll put over here. And 4, which was the main program, we'll put over here. In other words, we can take all the parts of the program and spread them around in the memory, and that way we'll be able to utilize those fragments. Now, just I want to point out, this is not like that we're going to do the segmented memory in addition to contiguous. We're not going to do contiguous at all. We're just going to do every program as pieces. And then we'll have to keep track of where each piece begins and ends. So it's going to be more information that needs to be maintained on each process. So what is that information? We need to have a segment table for each process, which contains the base and limit register, the base and limit values, let's say, for the start for the for each segment. Contains the start, right? The base contains the starting physical address where the segments reside, and limit is the length of the segment, just like we had before. But now we're going to have many of them, one for each segment for each process. Segment table base register points to the segment table itself. Now, the segment table is a piece of memory, so it has to also have a location of memory. So we'll have a segment that will have a special register, which will point to the beginning of that of the segment table base register, because we're going to have to access it all the time, and we'll also have a length, and we'll check then make sure that that we don't go beyond the end of that table. Okay. Now, well, we'll talk more about the tables later, but the tables have in them actually memory that is not allocated. With each entry in a segment table, you have to have some that are marked as 0 that you're not allowed to go to that segment, and some that are marked as valid. Protection bits associated with segments, code sharing occurs at segment level. In other words, I could actually have code sharing, because we said before, this square root is what is it? It's a library function. So this segment of my program could actually be shared with another program. It could be the two programs use the square root function or use the math library. So I could actually have that this segment is let's say read only. Nobody's going to be writing to it, and it's shared. Everybody can jump to that location and read the data there. Nobody can change it, but everybody can run that. So that will actually mean that I can save space, because any library function that's used by multiple programs will only reside in memory in one location. And that I gain by doing this segmentation. Since segments vary in length, memory allocation is dynamic storage allocation. So is a dynamic storage allocation problem. What does that mean? We still have our questions of best fit, first fit, and worst fit. That's what they mean by that, dynamic. In other words, they're variable lengths. So where I choose to put a segment, I may have multiple possible places to put a segment. I may put it in the biggest hole or the smallest hole. I still have holes, and I still have to find where to put a segment. Okay, that's the idea of segments. So here is your diagram. For example, I have, let's say, an address. The CPU says, go to this address. This is 1110011, whatever, some numbers. Now, actually, the address from the CPU's perspective is, let's say, 32 digits of ones and zeros. But we're going to say that some section of them, I'll just say, for example, 16 bits. The first 16 bits we're going to label S, and the second 16 bits we're going to label D. It could be, any number. It could be 8, the first 8 bits, and the next 24 bits are D. Any way you want to divide it is possible. But let's say let's just make it simple. 16 here and 16 here, assuming a 32-bit memory location. Now, the S is going to say that's going to be the segment number. In other words, that he just views it. The CPU just views it as a number, as an actual location in memory. But we're going to have hardware that's going to look at the first 16 bits and say, I want that to tell me where, which segment it is, which means go down this many lines in this segment table. If this number is like 100, they go down 100 lines in the segment table, and that will be the storage location of the base and limit register that I need. And then I'm going to use that in my, what we called the MMU before, in other words, in my hardware that checks to make sure that it's a legal address. And I'm going to say, first of all, is this less than, is the rest of it less than the limit that has been recorded here in the table? If it is, then he hasn't gone too far. Then take that address and add to it the base that's been recorded here. And then I know where to go. And I know where to go, which segment to go to, and where it is in the physical memory. Now, we said before they're going to be invalid bits, which are not written here. But basically, it's possible that this segment number will be for a segment of another program. So actually, this segment table is going to be one for each process. It's not just going to be one for the whole computer, because then then my program could generate a segment that's somebody else's segment, and then I could go and read it. Even, because I would go to his segment and I would get the limit there, and I would, use my D. I'm only checking the D against the limit on the base. I'm adding the base to the whole thing, but I'm only checking the limit against the D. And I could access somebody else's segment. So what we're going to do is actually duplicate this segment table for every single process. And for most of the rows in the table, there will be a 0 indicating that it's invalid, that I'm not allowed to go to that place. And only if the segment that he chooses is one that he's allowed to go to that doesn't have a 0, that's a valid row, then we'll take out from it the limit register and do all these checks and continue on. So the segment table is, again, like I said, it have multiple ones for each process. It could be that if this is hardware, if this segment table is hardware, which it is, that means that, so how you can have multiple ones? You're not really gonna have multiple ones. What you're gonna have is whenever there's a context switch, we're gonna copy the segment table for that process into this segment table hardware. So there'll be a part of the context switch will be rewriting the whole segmentation table, including all the invalid rows and all the valid rows. And then once we're ready to go, we'll get a memory location and we'll go to the segment and see if it's valid and then continue on with our checks and then access the memory. But once it's been loaded into the segment table, it'll be fast, because once this data has been loaded, then it's there and our hardware will run very fast. Okay, so that's the idea basically of segmentation. But this idea, the segmentation hardware, it suffers from one problem really, which is that we still have a fragmentation. Because even though I said that we can now squeeze smaller pieces into segments, because in other words, we have smaller holes, so we have smaller segments, and we can squeeze them into those fragments, into those little spaces in between processes, memory allocations. We can squeeze in now a small segment, but when we remove them, we're gonna have little spaces now that are available, and then as time goes on, we're gonna have thousands or hundreds of thousands of little slivers that are getting smaller and smaller now, because whatever I allocated, and now there was a little gap between that and the next one, and then that sliver is unallocated, and I'm going to get all kinds of tiny slivers, and I'm still going to be left with a lot of external fragmentation. So this doesn't really solve anything. So the actual solution is going to be with something called paging, which says, do I have a diagram of it? Well, paging says that I am going to take all my memory. You see, instead of here, where you see some sections are big and some are small, we're going to say, take all of our memory and in our heads, let's say, divide it up into equal units. So for example, if our memory is 100 megabytes, I'm just going to give a very simplistic example. If our memory is 100 megabytes, we're going to divide all our memory into 100 pages of 1 megabyte each, or even better, 200 pages of 500 megabytes. So we have 100 megabytes of memory. Remember, we're talking about memory, RAM memory, not disk space. So we're going to divide it into 200 slots, where each slot is exactly the same size. And then if I have, let's say, a program that needs 10 megabytes, I will give it 20 slots, but they won't necessarily be contiguous. They'll be anywhere in the memory. So now I'll never have any external fragmentation, because every program will be divided up into half a megabyte units, and I'll always be able to find, and as long as there's available space, it'll always be no smaller and no bigger than a half a megabyte. So if I have all of a sudden comes a program that needs 2.5 megabytes, I'll give it 5 slots anywhere, 5 different slots, 5 slots spread out through memory. And I'll always be able, and I'll never have a sliver smaller than that, and I'll never have a sliver larger than that. But that's okay, because my programs are always going to be divided up anyway. So that sounds great. Problem is, I can no longer use this hardware. I can no longer use this simple hardware and just say, what's the limit? Add it and go to that place. So is it less than the limit? Then add the relocation register to whatever memory. If you gave me memory 10, then I'll go to 200,000 plus 10 and go over here. Because it could be that he gives me 10, but he gives me 200. It could be that it's a totally different location. I need a new relocation register for every single, what we call, page. So we're going to actually create something called a page table. And that's what I talk about over here. So let's discuss paging. Let's read what's written here. The physical address space of a process can be non-contiguous now. The process is allocated physical memory whenever the latter is available. As long as there's available memory, we can use it. It avoids external fragmentation. Avoids problem of varying size memory chunks. We're never going to have varying size memory chunks. What we are going to still have is internal fragmentation, which is important to understand. Because if I have a program that needs 1.25 megabytes, I'll have to give it 2 pages for its first megabyte. And for the 1/4 megabyte, I'll need to give it a full 0.5 megabyte. But it only needed a 1/4 megabyte. So I've allocated to it memory that it can't use, or it's not intending to use, and yet it's been allocated and nobody else can use it. So I have something called internal fragmentation. But internal fragmentation will never be more than 1 page per process. And as long as the page size is not too big, then the internal fragmentation won't be that great, right? The worst case scenario would be it's 1 byte in a page. I needed 1 more byte, so I have to allocate it a whole nother 0.5 megabyte. So we want to keep the pages small. So actually, when I said a 0.5 megabyte, well, it's possible. But we're going to talk a lot about pages that are really small, like 512 bytes, 0.5 kilobyte. And we're going to call these, I call them pages. We're also going to call them frames. Why do we sometimes call them frames, sometimes call them pages? So when we're talking about the logical memory, the memory as the computer program sees it, he thinks of it as a page. But when we talk about dividing the memory of the actual memory of the computer, we call it frames. Now, the operating system is going to have to keep track of all free frames, which means frames in the memory that are unallocated. To run a program of size n pages, you need to find n free frames. In other words, it's n pages in logical memory. That's how big it is. So we need n frames in the physical memory, and then we need to load it into those n frames. We need to set up a page table to translate a logical address to a physical address, because we can't just have a simple mechanism like we said before of a relocation register. We need, for each page, we need to know where it starts. The backing store, the disk drive, will also be split into pages. And like I said before, we still have internal fragmentation. So Now we can talk about some theoretical things about the page. Well, here, first of all, let's look at this picture, and then we'll go back. The CPU is going to, again, create an address. Let's say it wants to go to location 100. So it's a bunch of ones and zeros over here. So from the perspective of the CPU, it's just address 100. But we, in our hardware, are going to look at that address and say, wait a minute. We're going to chop it in half and say, or half, or it could be, like I said before with the segments, it could be any amount. But we're going to say one part of the ones and zeros is called P and one part is called D. So let's say it's half and half. Let's say it's a 32-bit address. The first 16 bits are going to be what's called the page number. Because here is my page table. Again, there's one of these for every process. So the page table will say like this. If this is 16 bits, go to, and this number is, let's say, if I just look at those 16 bits in isolation, there'll be also a number. They'll be equivalent to a number. So this whole number could have been 100, but the P value could be, let's say, 8. So that means go down 8 rows in the page table, and you'll find there written a number. And whatever that number is, let's call it F, and we'll append that number F to whatever the 16 bits at the other side of the address were. And why do we call it P and F? P is the logical page, and we want to translate that into a frame number. So the 16 bits over here will be the frame number, and that will tell us where that address is in logical memory. In physical memory. This was a logical address. This is a physical address. So if he asks for PD, we're going to go to FD. Location, which means physical from the beginning of memory, down, 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 till we get to FD. Which is essentially, the beginning of page F, or frame F, is F0000. And the end of it is F, whatever F was, 11111. So somewhere in there is D. We don't know what D is. D is, it's a set of ones and zeros that is not, that could be all zeros, it could be all ones, it could be something in between. And what about if he produces an address that is not allowed, that's somebody else's page? Well, we are going to have in our page table a lot of zeros and ones, like for a validity bit. Now, there's going to be one more bit on vertical. It's not written here, but imagine a row here, a column going down, that every row has one more bit telling it 0 or 1. Is it valid or invalid? And if the CPU generates an address for a certain process that has a 0 in the valid bit, then we will not let him go there. So we also could protect other processes' memory from this process. So let's go back and look at this picture here. And here we're just saying, we're defining that P and that D. And we're saying the P is the page number and the D is the offset number. We call it the offset, means within the page, how many bits to go forward from the beginning of the page. Right, the page offset D is combined with the base address to define the physical memory address that is sent to the memory unit. Well, it's really the logical address that's sent to the memory unit, and the memory unit is going to produce, the MMU is going to, whatever we call this physical setup will produce the actual address. Okay. Now we can say interesting things. For a given logical address space of 2 to the m and a page size of 2 to the n, in other words, this whole thing is m bits. This is m bits. So we can say like this. Take off n bits for the offset, then what you're left with is that P is m minus n. Now the page itself, the page table itself will need to be contiguous. This is a disadvantage, but so far we can't avoid that, because how are we doing this? This P is telling us like 9, so it says go down 9. But it could be 16 bits. It could be like a very large number. It could be like, in the tens of thousands. So that means this page table is going to be very large. It's going to have many rows. And this P is just going to tell us how far to go down in it. So this one is going to be larger than a page, perhaps. And so this page table will have to be put in memory somewhere, and it itself will have to be in kind of variable, or fixed. I mean, it'll have to be in something that is not paged. It'll have to be in some memory that has not been cut up into frames, because this has to be contiguous. I mean, it could be cut up into frames, but we're going to ignore the frames. We're just going to the beginning and then going forward without checking any kind of page size limit. Okay. There will be a page. So the page table itself will need to be contiguous. There will be a page table for each process, like I said, because some of the pages will be invalid for each process. For a given local, okay, we said that. Each page table will be big enough to map every page on the system. Right, so we're going to have large page tables. Many pages for a given process will be marked as invalid because they have been assigned to other processes. In fact, most of the rows in the page table will be invalid because probably there's other processes using a lot of the memory. Unless, you're this huge process that's using almost all the memory, then most of your rows in your page table will be invalid because they're referencing they're referencing frames in memory that are not yours. Here's an example. So we have our logical memory, and my process says, my process uses these four. My process is contiguous. In other words, this is from his perspective, a jump command, like an assembly jump command, will go ahead 10 lines, it'll go to this page. And then another 100 lines, go to this page. In other words, they're all I can jump forward and backward in a contiguous space. But really, in the physical memory, 0, 1, 2, 3, they're all spread out. How do I, in fact, find them? By this page table, which says, if you want 0, go to 1. If you want 0, go to 1, page 1. If you want 1, go to 4, go to page 4. If you want 2, go to page 3. See, it's page 3 here is where page 2 is sitting. Frame 3 contains page 2 of logical memory. So that's our page table. Of course, this page table is very misleading the way they drew it here, because I just got through explaining that actually the page table has rows for every possible page in the physical memory. Right? If you look over here, this P is telling you which page to go to of all the theoretical memory. In other words, if I want to go to, it's true that there is a page 0, 1, 2, 3, but there's also, this page table keeps going. It keeps going to, in the thousands of pages if they're small. If the pages are 500 bytes, 512 bytes, then the page table is going to have many, many rows, and we're just showing you a beginning of it. Okay. So that was one paging, and here's another paging example where we say at memory location, in other words, here's A, B, C, and D. These are the actual memory locations for page 0. So this is my program. These are, let's imagine this is like a very simplistic, here it says n equals 2, m equals 4. In other words, it's a very small pages. Let's say each A, B, C, and D, that's this, in other words, that's the possible memories. There's only 4 pieces of memory, 4 pieces of data in each page. Each page is just 4 lines long. So notice I don't have anything written here about what a page, but this is obviously the first page. This is the second page, the third page, and the fourth page. So from 12 to 15 is the fourth page. So when I want to get, let's say, 12, that's the 0, 1, 2, it's 0, 1, 2, 3. That's page number 3. So I'm going to go to page table, and I'm going to go to 3, row 3, since that's page 3, and I'm going to see a 2 there. The 2 tells me go to row 2, or not row 2, but 2 times 4, which is 8. 2 times 4, which is, because 4 is the number of rows in the page. So 2 times 4 is 8. So I go to 8 over here, and lo and behold, there's my M, right? I wanted to get this M, which is sitting in line 12 of my code. But I know that line 12 of my code is my logical 0, 1, 2, 3, third page. So now I take 3 and I go over to the page table, go to row 3, and I see a 2 there. That tells me it's actually page 2, but each page is 4 lines long, so the actual memory location is 2 times 4, which is 8. That brings me to this 8, and then I get my M. So that's how I'm going to actually translate my logical memory of my program, which seems to be contiguous, to spread out pages in physical memory by the means of using this page table. Okay. Now we can get complicated examples with numbers here. Imagine a page size of 2,048 bytes and a process size of 72,766 bytes. So how many pages do I need? So it's very simple. I take the 72,766 and divide it by my pages. 2,048 is my page size, which is essentially 2 kilobytes. So I divide it, and I get 36, or I get 35 and a half, or something like that, which means I'm going to need 36 pages. That's what I have, 35 plus some extra bytes. So I'm going to need 36 pages. So I'm going to have what's called internal fragmentation because it didn't fit exactly. I needed an extra half a page. So what is that? I take the page size, subtract the extra bytes that I needed, and I have 962 bytes that are allocated to me, but which I don't need. So that's called internal fragmentation. The worst case of fragmentation would be the frame size minus 1 byte. In other words, if my frame size is 2,000, or my page size is 2,048 bytes, so the worst size would be 2,047 bytes of wasted space. On average, fragmentation will be half the frame size. Why? Because sometimes it'll be a tiny bit, sometimes it'll be a large. Sometimes this number randomly will range on this range. It will go from 0 to 2048. And as the extra amount, I can never know how long a program is, so it could logically be anywhere. So on average, it'll be exactly half. So it sounds like small frames would be desirable. So that's true from this perspective for limiting internal fragmentation. But each page table takes an entry of memory to track. In other words, our page table, as we make our pages smaller and smaller, we're going to have more and more rows in our page table. I mean, here we only have 4 rows because our memory was tiny. But if we had gigabytes of memory, then a page table where each page is only 4 bytes or 4 units, whatever, even if it would be 4 times 4 is 16 bytes, we'd need millions of them, and it would be huge amount of memory wasted for each process on its page table. So that's what we're going to calculate here. Page size grows over time. Oh, that's just, okay, we're going to calculate. We're going to calculate later. But page sizes grow over time, which means that in the beginning, like 20 years ago or 40 years ago, pages were small. Let's say 4 kilobytes, 8, or it could be 4 kilobytes or something like that. Actually, here it's saying that Solaris has 2 page sizes, which is very unusual. But you can have a 8 kilobyte or even a 40 megabyte very large page. Process uh, view and physical memory now very different, right? In other words, the process views its memory as contiguous, but the physical memory is not contiguous. There's no connection really between the logical memory and the physical memory. Okay. We're also going to have to keep track of free frames. So, for example, our free frames are these gray ones, which means 16 is available. I'm sorry, the gray ones are the free. 16 is being used by another process. And now comes along a new process, and he sees and the operating system sees a free frame list, which is 14, 13, 18, 20, and 15. I mean, the list is not in order here. Those are the free frames. Now, if a new process comes along and he says, hi, I need pages for my page 0, 1, 2, 3, and 4. So we're going to stick them places, and we can stick them anywhere. Here we stick 0, 1, 2, 3. And then we're going to build a page table for this new process. And it will say like this: 0 page is at page 14. It's at location 14. 1 page is at location 13. And that's his page table. Right. Of course, we don't have all of the, this page table could be a lot longer, like I said. All right, we'll talk about implementation of the page table in the next lecture.